Thank you. Thank you. Thank you. All right. When to refactor your code into generators and how. So the goals of this presentation is that after this presentation, you will be able to recognize certain loop constructs that as candidates for refactoring. And you will know how to refactor these constructs into more maintainable, elegant Pythonic code. And you will have had your first acquaintance, perhaps, with the standard libraries itertools module and the wonderful more-itertools package, PyPI downloadable. But first, let's introduce myself shortly. My name is Jan-Hein Buhrman. I'm the author of Basic Python for Java Developers tutorial on the real Python. And 32 years ago, I witnessed the first baby steps of Python up very close at the CWI, the Dutch National Research Institute for Mathematics and Computer Science, while Guido was working on his first versions of Python. It was very nice. And while in the next step of my career, so I was mainly working as a C and C++ developers, sometimes I was able to pull in Python for certain, to use it for my work. For example, to help automating testing my C programs. My employer is Ordina. It's a Benelux IT service provider. And when I was a Java unit manager, I came up with the idea of starting up a Python practice. And this practice focuses on Python combined with software artisanship. And the last couple of years, I do what I like most, and that is Python programming. So the topics of these presentations are, I will introduce you to a family of similar functions, and they involve loops, and they contain fragments of similar code. And I will show you how you can identify distinct responsibilities within this seemingly entangled code. And I will touch upon the topic of generator functions, and how these generator functions will enable you to refactor this entangled code into separate functions. And finally, I will introduce you to the utility generators and functions from the itertools module in the more-itertools package. So I'm going to tell you a story. It's a fictional story, it's not a true story, about a Python team that will develop functionality for a product owner. And this product owner is representing the Fibonacci sequence fan club. And the product owner would like you to make a function returning a list of all Fibonacci numbers up to a certain threshold, let's say the value n. So first of all, who knows what the Fibonacci sequence is? Many n's. Quick recap. The Fibonacci numbers form a sequence, the Fibonacci sequence, in which each number is the sum of the previous two. And you start with the first two numbers. Usually they are 0 and 1. And the next value is obtained by adding the two previous values. So in our example, if you start with 0 and 1, the next value is the sum of those two values. So the next value is 1 again. And then the next value, then you add 1 and 1 together. So the fourth value is 2. And 1 and 2 makes 3, that's the next value. 2 and 3 make 5, etc., etc. And that's how you are building up this Fibonacci sequence. So a bit of Googling might bring you to Python's own documentation site, where an example Fibonacci function is shown. The implementation here has another name. It contains type annotations, it contains a docstring, but in essence it's the same function as from the Python documentation. And I will give a short explanation of how this function is working. First, you initialize a container that contains the result. And the container is a list of numbers, and you start with an empty list. And the next step is that you initialize two variables. They are initialized to the two first Fibonacci numbers, 0 and 1. And you could see these variables as Fibonacci registers. So the first variable, variable A, contains the current Fibonacci number. And the other variable, variable B, you can see that as the value containing the next Fibonacci number. If you remember that, then it becomes more clear. And if you then look at the code, you enter a while loop, and as long as the current Fibonacci number is less than the threshold value, you start calculating. Then you first append the current Fibonacci number to the resulting list, and in the next step, you start calculating the next pairs of A and B registers, the current and the next Fibonacci number. And you use Python's elegant feature named sequence unpacking to do that. So in one go, you calculate the new A, which is the value of the old B, and you calculate the new B, which is the sum of the old two A and B registers. So that's how it works. And, well, your team demonstrates the functionality to the product owner, and he's happy with the result. So now he asks us to make a function that returns the nth Fibonacci number, zero-based. So Fibonacci number 0 is the first Fibonacci number. Fibonacci number 1 is the second Fibonacci number. But he makes it zero-based just to facilitate us programmers to make everything zero-based indexed. So let's code this new feature. Here you see the function again, fib ordinal, and here you see you don't see the initialization of the list because you're just returning one value, but you see the initialization again of the two Fibonacci registers, 2, 0, and 1. You see another loop, not a while loop, but a for loop, and this is a counting loop. You are using the range function just to count the number of iterations that you want to go through. And you are narrowing the return value of range, but then you know how much iterations your loop is executing. And within the loop, you're just calculating the new set of current and next Fibonacci numbers. And at the end, when the counter is exhausted, you return the current Fibonacci number. So you demonstrate it again, and now the product owner really gets enthusiastic and requests us for 2 more functions. Product owners never get enough. More functions, more functionality. So the next function that he would like to see is a function that returns the first n Fibonacci numbers. It's a little different from the first one. Remember, that one was up to a certain threshold, and these are just the first n numbers. And finally, he wants us to make a function that returns the smallest Fibonacci number equal to or greater than a certain value. So first, let's quickly look at Fibonacci function number 3, the first n Fibonacci numbers. Here we initializing a list again, holding the result. You have the initialization of the Fibonacci registers again. You have a counting loop here as well. You fill the list with the current Fibonacci number. When the number of counts is executed, of course you calculate the next Fibonacci numbers, and then you can return the resulting list. And finally, let's go through that one quickly as well. Return the smallest Fibonacci number greater than or equal to n. Here you have the initialization of the Fibonacci registers. You have a while loop, and as long as the current Fibonacci is smaller than a certain threshold, you just calculate the next set of Fibonacci numbers. And when the condition no longer holds, then the current Fibonacci number is either equal to n or greater than n, and then you can return the current Fibonacci number. Well, 4 functions is enough for now, I guess, to make my point. And I've collected them here without the type annotations and without the doc strings and with shorter names and stuff. You see them here in one slide. And I guess we are seeing some sort of pattern here, right? Who sees a pattern? Many people see a pattern. That's great. And what's the pattern? Well, the pattern is that most of the times, or sometimes, you first initialize some sort of container that will hold all the values that you want to return. So those are the functions that return a set of numbers, a list of numbers, whatever. And then you see this now familiar initialization of the Fibonacci registers. Then you enter some sort of loop. And then sometimes in this loop, you need to fill this container with the current Fibonacci value. And always, you calculate also the next 2 Fibonacci numbers, the A and B registers. And at the end, you either return the then current Fibonacci number, or you return the resulting container, the list that you've been building up in the function. So, now that you see that the same code appears in multiple times in the different functions, you start looking for ways to get rid of this repeated code, because you want to keep your code dry. I don't know how you experience it, but I always get these itchy feelings that when I'm typing the same lines of code, I want to refactor it and want to extract the common part into some sort of functionality. So you start looking for ways how to refactor the code, extracting the common part into a method or a function, whatever. So first of all, who knows what refactoring is? Is everybody practicing refactoring as well? I guess many people do. Great. And when you try to refactor this, normally you select an adjacent couple of lines of code. If you have a very intelligent IDE and you say refactor this, and then it starts, it invents a method for you or a function, and then you're sort of done already. But that seems impossible with this kind of code, because I'm going a little bit too fast here because my slide is saying something else. First, let's dive a little bit deeper into refactoring. So, what is code refactoring about? Well, it's about restructuring your code without changing its external behavior. So you usually do this to improve the design, the structure, and implementation, but you make sure that the original functionality remains the same. And in that way, you do that to make your code more readable, less complex, and better maintainable. So that was a little backtrack. Now, fast forward again. It seems impossible to factor out the common parts in this scenario in two separate distinct functions. The code is mixed up with control flow constructs, and that sort of makes it impossible, especially the loop constructs, to make it impossible to extract the common part of the code that you want to extract. So you're stuck. You don't know what to do. As a last resort, you could think of, perhaps I should combine all the functionalities, all the function in one golden super function. And then you have some sort of enum that designates the mode for what you want to calculate for that particular function. We could try that experiment, not with an enum mode, but let's try to combine the first two functions. And then there is a Boolean that indicates whether you want the first n Fibonacci numbers or the other function. And I have to warn you, perhaps it's good to put you on your peril-sensitive sunglasses, because the code that I will present to you really hurts the eye. As you can see, it starts already with the ugly type annotations. And Lukáš Bukáš-Langa, the author of Black, was also mentioned in the previous presentation. He stated in the PyCon keynote of 2022, ugly type annotations are an indication of ugly code. Well, I think this sort of proves that. And you should not take this contrived example too seriously. It merely demonstrates that the resulting code is not quite the way to go. It's not maintainable. So we have to think of another way out. I don't try even to explain what's happening here, right? It works, but it's terrible. So you're stuck again. What else can you do? Well, if you feel the urge to refactor in code involving loops with repeating stuff, then the first step that you can do is to look at your code at a more conceptual way, from a larger distance, at a higher flying altitude, so to say. And then you realize that there is a dating producing part in your code, and that's the code that is calculating and providing the Fibonacci numbers. And there is a data consuming part, the code that either collects these values in a container or is checking some condition that identifies the moment to return the then current Fibonacci number. And the data producing part is the part that you can isolate. But before we can do that, I need to introduce you to another concept, and those are generator functions. And a generator function, in short, looks very much like a normal function, but instead of that it contains a return statement, it contains yield expressions, or it contains a yield expression in a loop. A normal function, if it wants to return multiple values, it collects them in a list or something like that. A generator function returns, between quotes, the value one by one. It gives a value back to the caller, while the function itself remains alive and is waiting for the next number, the next thing that it can return. To show that, let's make a very simple example generator function, mimicking the behavior of the range function that you all know, when you would call it with a value of 2. When you call this function, so here you see the implementation, right? It doesn't contain a return statement, but it contains 2 yield statements. It yields the value 0 and then it yields the value 1. And it contains also, it's larded with some print statements so that you can see what happens when. So first you need to create this iterator. This is the iterator protocol that I'm explaining right now. And first you create the iterator by just calling the function, and then you get, the function produces an iterable for you. It's called a generator iterator. You get an iterator from it. And if you want to obtain the first value, you can call next on it. And what you see happening then is only then it starts executing something within the function, because you see that because of the print statement. And then it yields the first value back, and then it immediately stops again. And if you want to obtain the next value, you call next on it again. And then you see that only then it starts continuing again with executing, and then it returns the next value back, the 1. And finally, if you want to obtain the next value, then you get a stop iteration exception. But that's completely according to the iterator protocol, so that's quite normal. And actually, when you use it in a for loop, the for loop is handling this iterator protocol for you. If you would use the for loop, then it works perfectly fine, right? You see the prints again, and you see the values, and the for loop within Python under the hood is managing this stop iteration exception for you. So now that you know this, how could you implement a Fibonacci number? Well, I'll just show it here. This is the Fibonacci number generator. I call it FibGen. And as you can see, it's very basic. It only contains the initialization of the 2 Fibonacci registers. Then you enter a loop. And in this case, you enter an n plus loop. And the first thing you do within the loop is when a value is requested, you yield the current Fibonacci number. And once the next Fibonacci number would be requested, the loop continues. You calculate the next set of 2 Fibonacci registers, and you can yield the next value. And this is how the Fibonacci number, the Fibonacci generator function looks like. So how can you use this with the previous functionality? For example, if you again want to give back, for example, the first number of Fibonacci numbers, how can you use that in combination with this generator? Well, a very straightforward implementation is by combining it with a range function again, zipping them together, and then you ignore the value that you get back from the range function. That's not so interesting, but you can use the value that you get back from the Fibonacci generator, and that's the version that you can print. And the function stops after the requested number of iterations, because the zip function stops as soon as one of the iterables is exhausted. There is no more value to return. So that's the reason why it is stopping after 8 iterations. So this could be the end of my presentations. We are set. We have a Fibonacci generator. We can code the other half of the functionality by hand, by, for example, using zip or some other things. So using some condition to check the returned value. And then you're set. But there is more to it, because you can also eliminate these explicit loops that you are coding. You can do that by using the functionality of the itertools module, which is part of the standard library of Python, or sometimes Also, there is another PI downloadable package, more-itertools, that can also provide some convenient functions for you to use. A massive amount of convenient functions. I just discovered a few new ones very recently. So first, so how would you implement the first function? The Fibonacci number is less than a certain threshold. Well, first then I need to explain to you shortly the iter-tools take while function. And this function, or generator, or filter, whatever you like to call it, takes an iterable, in our case the Fibonacci generator. No, it first takes a predicate function, and the predicate function returns a Boolean for a certain condition. And the function that it receives is the current value that it gets from the iterable. And in our case, that would be the Fibonacci generator. And the take while just passes on those values from your generator as long as the predicate holds, as long as the predicate is true. So then the function is reduced to this one-liner. So the predicate function is this lambda expression, your current Fibonacci number, as long as it's less than the threshold that you provided. You pass on these values from the Fibonacci generator, and you collect them in a list, and then you return the list. So that's the first function reduced to this one-liner. The second function, I need to explain first a few other functions from you. The iSlice functionality from iter-tools. You can compare iSlice with slicing, list slicing. You know, when you have a list, you use these square brackets where you can provide a start value, a stop value, a step value, and you compare. This tries to do the same, but then on iterables. The functionality is less rich because you cannot provide negative numbers, but it still does what you need it for in this particular example. And there is another function from the more-itertools package, which is called one, and that function checks whether the iterable contains exactly one value. If it contains less, so you have an empty iterable, then it raises a value error. If it contains more than one value, it raises a value error as well. You can provide other exception classes if you would like to. And if you use this functionality for this n Fibonacci number functionality, then you get this. You call fibgen and you slice it starting at index n, and you end just before n plus 1, which means that you get exactly one value back. And the more-itertools.one extracts that one value and returns it to the caller. Well, likewise, there is an implementation for the first n Fibonacci numbers. You use iSlice again, but then in its basic form with just a stop value. You can check it out yourself later on. So I stop explaining because of the time. I'm running 2 minutes after the schedule. And the final function, there you can use, instead of take while, you use drop while. And drop while does sort of the opposite. It drops values from your generator as long as a condition holds. So in this case, and then you use first to select the first item that the drop while is returning, and then the iterator ends. This is the implementation. So again, you have a lambda expression. The expression tests whether the current Fibonacci is still less than the desired value as a threshold. And you drop the values as long as they are less than that value. And then, when the value is either equal to n or greater than n, it starts producing those values and give them back to the caller, which is more-itertools first. And more-itertools first just selects the first value, it returns it, and it stops the iterator. So I hope that I was able to demonstrate how you can use these tools and the generator functionality to make your code more expressive, simplistic. And I encourage you to read through the documentation of the iter-tools module and the more-itertools package. Just get a grasp of what they are offering, because there's a lot more. As an example, the more-itertools also provide a chunked function. A chunked can be very convenient when you are ingesting or importing or filling a database with massive amount of data. And sometimes you just have to draw a limit because your ORM or your database driver cannot handle all the values in one go. So then you can use iChunked or chunked that collects a certain amount of records that you can process, and then you can send that batch of records as a batch to your drive or to your database, and then it starts collecting the next batch. So that's just an example of the many useful utilities that can be found in this wonderful package and library. So you've heard about the following. I think that we are now able to recognize the pattern of certain loop constructs as candidates for refactoring, and that you can use generator functions to extract the data producing part. And the third takeaway is that iter-tools and more-iter-tools might save you a lot of coding. These are the resources and links for some of the quotes that could be found in my presentation. And I would like to thank you for coming and listening.
Thank you. Are there any questions? Yes, in the back.
You mentioned having an iter-tool stuff first. But
Yeah.
is that able to backtrack into your generator to get the true first item to generate in the ever generator, or is it similar to next and then it gets the first next item that you waited?
No, yeah, a generator is gone, a value is gone as soon as you have consumed it. So if you have a semi-used iterator, and then suddenly apply first to it, then it will provide the first value of what is then left in the iterator. But there are other tools that can, for example, remember all the values that have been passed. But of course, that's more memory consuming. But there are tricks that you can rewind your iterator and replay it again and stuff like that. It's awesome what you can do with all these tools.
Anyone else? Yeah.
Isn't first the same as next, or what's the difference?
Actually, it is, but next, I view next perhaps as I don't know if it does exactly the same. The difference is that next can give you an exception, the stop iterator exception. First will give you a default value if you provide it. So that's a little difference. And I think that next is clearly part of the iterator protocol, perhaps a conceptual lower layer than the conceptual first, which is more on the end programmer level to use. Yeah.
Anyone else? Yep, one in the back.
I was wondering, just generally, I guess that iter-tools and more-iter-tools never really kind of handles the code inside the iterator, right? It's always about kind of working with the iterator on the outside layer, say, right?
True. Yeah. Perhaps I should. Well, okay. So the question was whether it really interfaces with the low-level iterator functionality of the Python code. So no, it uses the iterator protocol to provide its functionality. Yeah.
Well, we have time for one more question. Anyone else? Well, I'll ask a question then. Do you have any advice for someone who has never gotten into generators but would like to make use of them? Just some advice for someone beginning out?
Well, personally, but that's a really personal matter of taste. I like the real Python side a lot with the tutorials it offers.
Yeah.
And when I have had a wobbly career. I have been programmer, I've been manager, but when I went back full to 100% being a Python programmer again, I'm such an old-fashioned weirdo that I just read the Python standard library from A to Z.
Right.
To make me acquainted. I knew it already a little bit, so it was a lot of aha erlebnissen. But yeah, just start reading, and
Yeah.
it also already the standard library and the Python documentation is of excellent quality.
Of course.
But that's a bit old-fashioned, I know.
No, it works, yes,
Yeah.
and that's the best way.
And a modern guy would say just Google around.
All right, well, thank you. Thank you. A round of applause for